Okay, so we've done 3 out of the 4 sections. Okay, I'll remind you what the program was for today. This morning was excitability, Turing patterns, Lyapunov functionals. We've done all 3 of those, and now we are going to do spatial analysis and fronts. And these are all topics having to do with various versions of reaction diffusion equations. Oh, I see I hadn't quite finished the Lyapunov function. Okay, so let me go back to that. I remind you that what we're trying to do with Lyapunov functionals is generalize this idea that if we have a gradient system, it cannot have limit cycles. But this system here had no spatial dependence. And we were trying to generalize it to this system where there is spatial dependence in the form of, there's no point in having spatial dependence if you don't couple the different points in space. Otherwise it would just be, each one would be evolving the same. So the usual thing, the usual coupling used is diffusion. So the question is, what about a system like this? Can it have limit cycles? Say, is it a gradient system? In what sense is it a gradient system? And we answer that question partly by defining a new kind of gradient called this Lyapunov functional f. And we went through a lot of trouble to show that we could write our equation. Our equation is, the equation we wanted to study was this one. Remember, originally we studied it without this term here, so we just had a gradient system, and we said, could we add some diffusion and it still be a gradient system? And we added some diffusion, and we defined this f such that it still was a gradient system in a certain sense, right? We see that it's like before, except grad phi has become this functional derivative. But we still didn't do the last bit of work. Is f going to change? Well, that's kind of what we had before. Let's see. Yes, over here, our argument for there being no limit cycles, we made 2 arguments. We said there's no Hopf bifurcation because there's no, these have real eigenvalues. But we were more general about that. We could show that phi decreased in time, which you might think might be obvious, but let's show it. Phi is a function of u at u1 and u2 and u3, and d phi dt phi is going to change in time through the values of u1, u2, u3. So we write these partial derivatives. Chain rule, okay. And this d phi du, that's the gradient of phi. Du dt, that is d phi du because that minus d phi du because that's the evolution equation, right? This first thing is the definition. This second thing is the evolution equation. So we see that this is minus grad phi squared. This is a scalar. It's negative. And we've shown that d phi dt is always negative. It always decreases. And it decreases monotonically, as we said, either to minus infinity or to a 0. Okay, let's show the same thing here. How is d phi dt, df dt? Well, we go back to the definition of the derivative. Excuse me, I shouldn't have written this little derivative here. That's a mistake. I should correct that. That's a delta t. Okay, so correct that in your. It's not a function, derivative. It's not a change. It's not a little functional change. It's just a delta t. Okay, u of t plus delta t is of course u of t plus du dt, delta t, etc. Usual Taylor series. Let us now expand f, and we write f of u of t plus a perturbation is f of u of t plus, now that integral with that df du, du dt, delta t, right? That's the Taylor series applied to f. We then, excuse me, and then we subtract from both sides there. So we have this integral here. Our differential equation is du dt is minus df du. So that becomes minus du dt squared. So we've shown that f, this functional, decreases in time, and hence limit cycles cannot occur. And for the same argument as before. You can't hang around at a limit cycle, you've got to be always going. And this all of this does not require, I mean, we did this on an interval, but we could have done it in any number of dimensions by replacing the various integration by parts by the divergence theory, Gauss's, all those, okay, where we would get really surface terms and not just boundary terms. So we could have done all this, and this would remain the case. Okay, so yeah, Gauss's divergence theory, right. Okay, so that's the end of that. Now we go to spatial analysis and fronts, and we are now going to consider this same kind of equation that we just considered here, except now we're going to consider it only in one dimension. This is not going to be generalized, and you'll see why in a second. Okay, so this is the same equation we just looked at. Let us seek traveling wave solutions. So instead of having u depend on x and t separately, it's going to depend on x and t via x minus ct. Of course, if c is equal to 0, then we're seeking steady states.
So in this case, you have a solution to the reaction diffusion equation that is a wave equation. So
so far, no. So far, we're just discussing it. Oh, no, excuse me, that's not true. I wrote traveling wave solution. That's right. No, we do. That's right.
So, well, it came to my mind that diffusion equation and wave equation are different in structure. So
yes.
Diffusion equation is kind of
It's parabolic.
And
the other one is hyperbolic.
Yeah.
Yes.
So what is this boundary that
wait till you
both
see what's going to happen. You're going to be very impressed. You are a perfect audience for what is going to happen.
Yeah. So you can. So yeah, this is interesting because you could have a wave equation for a parabolic equation.
Now, okay, let's see more general, without what's going to happen, which is kind of special case. I can say in general, look, you saw the movies, did you not, of the convection with the traveling waves going around. And that's Navier-Stokes equations. That is quite parabolic. You have that Laplacian in there. You have a traveling wave. So certainly, parabolic equations support traveling waves.
Yeah, in fact, it's not strictly parabolic because of the reaction term. So if we add that term, it's not strictly a parabolic system.
This is true, and that's necessary. You're telling me, you're thinking that if it were strictly parabolic equation, well, certainly, I don't feel that the heat equation supports traveling waves.
Yeah.
You need, if you put in a source term, if you put in an external source, would it still be parabolic? Let's say the derivative, the nature of the derivatives would not be changed. Could you have a source that would counteract that diffusion and it become a traveling wave? Maybe. I don't know. And what about what we just did? What about those reaction diffusion equations? They were, there was no sense in which they were hyperbolic. They only had diffusion, and yet you saw that they had traveling waves. You saw those movies and all, and there is no hyperbolicity in there at all. There's no first derivative. There's no sense in which they're a wave equation, and yet they did support traveling waves. So I guess I will say, with this little bit of evidence, that no, you need not be a wave equation to have waves. I mean, wave equation, you need not have a hyperbolic equation in that PDE classification into
so
three kinds of
you can
sense.
have traveling wave equation in parabolic
Yes,
equations.
I'll say you can. That's right. Because certainly, as far as the differential operators go, this is merely merely diffusive, and this is merely parabolic with a source term. Yes.
It's a very basic question. Since with the introduction of this term del phi by del u, the reaction terms or something, it's no longer a linear equation, right?
Which one? I mean, indeed,
This
we're
one.
not. This one. I mean, you're looking down.
Okay. I mean, this del u by del t is equal to minus d phi by du plus the diffusion term del square u by
This
Yeah,
one here,
this
yes.
one.
Mhm.
So
This
can
is-
we still do
This
the
is no
classi-
longer a what kind of
It's
equation?
not a linear, right? Because this phi term is like d phi by
But
d.
that's right, nobody ever said any of them were linear.
Yeah. So can we actually really classify then hyperbolic?
Ah,
That's
well,
for
maybe
linear
that,
PDE.
yes, possibly so. Maybe that's what keeps us from that classification. Certainly, with some kinds of nonlinearity, I know you can continue to make that classification. I have
Those
seen.
are very special kind of, as far as I know.
I've seen the method of characteristics used in nonlinear hyperbolic differential equations. I am not sure. You would have to ask somebody more skilled in these questions about that classification, when you can apply that classification. I've heard it said that some equations are hyperbolic in this domain and parabolic in that domain. So that certainly is possible. What makes them so, the exact criterion for being parabolic and hyperbolic, that you apply when the equation, I know what it is when the equation is linear. We know it's like with conic sections or so. We know this term is negative and that a minus bc or something is, that we know. But when it's nonlinear, I don't know what the classification is. It must be somewhere, maybe even Wikipedia or somebody. Okay, so here we are. We're going to seek traveling wave solutions for these equations, as diffusive as they are. And so we're going to substitute a traveling variable, x minus ct, for, call it zeta. And this equation then becomes du dt x of t, excuse me, the two terms become minus c du d psi, that's this red term, and the blue term becomes d squared u d psi. This is psi, isn't it? No, it's not. What is it? What is that term? What's that word? That letter? What do you call that one?
Which one?
This Greek letter. What's its
Right.
name?
Zeta.
Zeta? Really?
Yeah.
Doesn't zeta look like?
I thought it was
It's
psi,
not
like
zeta.
It's
Oh.
psi.
Okay, hold on. I know there's chi is like that. That's chi. To me is okay. There's zeta. No,
Zeta.
there's
I
no.
think
That's
it's
said no. Okay.
Zeta's like a
Yeah.
backwards
So
zeta.
what's this one then?
XI.
Psi.
Xi.
Zeta.
Is that what that one is? Yeah.
XI.
Xi. Ah. Yeah? General agreement? Okay. Anyway, so that new variable, that traveling variable, we can transform the above equation, which had two independent variables, x and t, into one that has a single one, xi, there. And so our equation becomes this equation. Okay. And recall that d phi du, the gradients are in terms of u, right, and not in terms of any spatial or temporal variables. This is like if you had u cubed here, like in Ginsburg-Landau equation or normal form, then this would be 1/4 u to the 4th, right? Okay. So we're going to just reorder it like this. And we're going to make an analogy between space and time. That's why I said you might like it. So this question of parabolic, hyperbolic. We're going to make an analogy between space and time. This is called spatial analysis. And for that reason, this x will have to be 1D. You see that we've written here x minus ct, and we've written c as a scalar, not as a vector. So we only know of one dimension for time. That's something for the physicists to work out. I know they're working 16 dimensions. Are some of them temporal dimensions? I don't know. But we are only used to one dimension for time. So this, as presented, applies only to one dimension in space, as opposed to what we just did. Okay, so we're going to make an analogy, and it's all. The math is trivial, but it's all going to be just work for the mind. We are used to thinking of our second derivative here as diffusive, right? As diffusion, right? Diffusion is you pass on your values to the next guys. But we also see second derivatives in the context of mechanics, where it's the acceleration. Okay, so suppose we think of this as an acceleration. The u is then like a position. And this, which depends, okay, du dxi becomes like a velocity, and this is like a friction. Each of these terms had very different roles before. It was diffusion, but now it's acceleration. And here I point out something weird. Remember before I said that, okay, here I have minus d minus phi du. So my acceleration is not going down the potential, I'm going up the potential. I have minus minus. Unless I view the potential as minus phi. And then this brings up something that I said before that nobody protested about, and that doesn't surprise me. I wouldn't have protested about it either if I were you, but is very wrong. I said before, look, this isn't surprising, or even back here, this is normal. We go down the gradient, right? We're going downhill. But is that Newtonian physics that we go down a gradient? That the velocity, this is a velocity that our u is a position, v is a velocity, du dt is velocity. We go down a gradient. Is that Newtonian physics? That's Aristotelian physics. The velocity doesn't go down, it's the acceleration, right? You don't have minus grad phi for the velocity, it's the acceleration. And I think it's something that, I mean, no wonder you didn't protest. It's not very intuitive. I think all of physics, ever since Newton, is not very intuitive. Of course you go downhill, and of course cars don't keep going, of course things don't keep going in the absence of acceleration. Everybody knows cars stop, right? What's this idea that velocity is conserved? No, obviously it's not conserved. The value gets slower and slower, right? Okay, and the reason for this, in my opinion, is that the way mechanics is taught, or was understood by Newton, is celestial mechanics. There's no friction. Our whole world is completely dominated by friction. And when you're taught physics, assuming you're taught in the same way I was and everybody that I know was, friction, well, we'll learn about that later. That's a complication, perturbation. You learn that your acceleration is proportional to the force, and in the absence of forces, that you have no acceleration, that your velocity stays the same. But everything in your experience is completely opposite to that. You know that to keep going at the same speed, that is a lot of effort. You are not on one of those billiard tables where somebody gave you a push and you end up at your residence just like that. You know that you have to keep going, you have to climb up, and it's a lot of effort. And it's strange that physics is taught in this complete way that's, it's taught to you, I'm talking about mechanics, I'm not talking about quantum mechanics or relativity or anything fancy like that. I'm talking about mechanics, which is supposed to describe our everyday experience. And yet, the way it's taught is completely opposite from your everyday experience. It's something that applies only to those hockey tables, right? You're talking about that have that air going up so that there's no friction. It applies to celestial mechanics. Okay, this I agree with. And I know that some people, they spend their time, they look up and they understand. I wasn't one of those people. To me, the stars, they're up there, that they move, is something I had to be told. I have no intuition about the stars. I have no intuition that they go around elliptical orbits, this and that. And yet, all the physics that you taught in the beginning is all like that. It's all frictionless. It applies only to celestial mechanics and to those special hockey tables. So it is not surprising that when I said to you here, oh, you go downhill. Accepted that, that's your experience. But that's not real physics. Real physics, the way we're taught it properly, is this, that we have an acceleration, a second derivative that is minus a gradient. The second derivative is minus a gradient. The acceleration is minus a gradient. Right? That other thing is not even dimensionally correct if you signed it. This one is. But, okay, again, now so that's the end of my little speech about everyday matters. Now let's go back to this. This is telling you that the potential is upside down. Now, that is not to say that in everyday life, we're all thinking about potentials wrong. We're not. The potential is correct. We do have higher potential energy when we're high than when we're low, and so on. It tells you that when you make this mechanical analogy and you take this second derivative and you turn at which was diffusion, and you turn it into acceleration, this thing here that was minus sign is going to need another minus sign. So in the mechanical analogy, where this has become acceleration, we now have changed the sign on this term. And what was our potential now is minus our potential. And you'll see that in a little while. Okay. So now all these terms you should recognize from the physics that you had. You know that a second derivative of something, which we're now going to call a position, is an acceleration. The gradient, and by gradient again, note where this is, u is like x, a position. If you take a derivative with respect to x, excuse me, you take a derivative here with respect to u, not with respect to psi, which has now become kind of like time. Okay, this is a gradient where this variable and this variable d squared x dt squared is d something d is minus d something dx. That's where true potential works. This minus phi is the potential. And we know that friction is proportional to the velocity, which is the first derivative here, with a coefficient, with a friction coefficient. And note that the friction coefficient here is what was called the wave speed before. Okay, so does everybody understand this equation as what they were taught in physics? With the friction term, the gradient term, the acceleration term. So those are the analogies. And we can write the energy now as minus phi. Remember before, this is different from what we did before, where we wrote, where we had our free energy was the phi. So we didn't make this this changing of the senses. Before it was phi. Now it's minus phi, but this is going to be true physics, the one that's not intuitive, the one that's full of friction, but it's going to be true physics. So minus phi is the potential here. And then plus 1/2 the velocity squared. What we've learned is the velocity. Okay. And so we just do some differentiation here. We have minus d phi du, du d psi. We have this is a derivative of a square, so but we have a half, so they go away, and we end up with the du d psi times the square. That's just the composition composition rule for derivatives, and we end up with du d psi, yes, outside as before. And here we recognize our equation. We have this term here, and we have this term here. We bring it over, and it will be minus c du d psi. This one here. We bring it over. So this is minus c du d psi squared, and that tells us how this thing that we have defined as the energy evolves. And we see that it does something that we know all about when c is positive, that's to say, energy decreases, or if c is equal to 0, it's conserved. But it increases if c is negative. Okay? So this is the first thing that tells you, wait a minute, this is an analogy, this is all well and good, but wait a minute, this is not really, this is not right. Because what is c? There's nothing fundamental about the sign of c. Look where c is. Right going versus left going. And there's no difference between right and left in this problem here. It's just this has a second derivative, which doesn't distinguish between right and left. There's nothing right. If the traveling wave solution, this happens to go to the right. Okay, this is just telling you to go to the right. And yet, this is telling you that energy is being created if you go to the left. Well, so this isn't really energy. So it shouldn't disturb you. These are just words. It just means that we can use all the kind of calculational tricks that you learned in physics, and when you called it energy and so on, you can use all those methods in this problem too. But don't be perturbed. Don't think, oh, energy is increasing. No. This isn't energy. This is just something you called energy, and it looks kind of like energy, and we'll be able to reason some from it. But you shouldn't be perturbed that it's anti-physics. Yes?
That is not anti-physics, like it just means energy increasing, that some external work is being done
Okay.
continuously.
All right. Okay. Good. That's a good physicist answer, and I'm sure that then if you look at this equation, you will figure out where the work is being supplied.
Yep.
Where's the work being supplied?
The friction term, if that becomes positive,
Yes.
it means that some external agent is continuously doing work which is governed by this law.
Ooh, maybe, but I don't see, I'm sure you're right, you sound very confident, but where's this external agent? This seems to be a self-contained equation. There's no force term in it.
I mean, somehow some anti-friction term is there. If C is
I'll
negative,
say, this is,
which
that's
means
right,
that
it is
there's something-
anti-friction, that's right.
Yeah.
This so-called friction is anti-friction.
friction means something, some dissipation, which means
This is anti-dissipation, that I'm going to
that
say.
would be anti-dissipation, means that something is trying to increase the energy of the system.
But that something is its own self. I'm saying there's no source here. This is, I believe, I'm not sure, but that this word friction is kind of being applied wrong. Friction, the word friction, the way we use it, is that we have something rubbing against something else. It necessarily you increase the velocity, the absolute value of the velocity, and you lose energy. This is something such that possibly it has either sign. So possibly you increase the velocity, and that makes you lose energy, or perhaps if it has this other sign, you increase the velocity and it absorbs energy. So it's not friction the way we know it. It's something that can take on the properties that you usually think of as friction if C is positive, but C can be negative, and we can gain energy from rubbing against something. So that you're satisfied with that? Yeah. But there's nothing external here. This is completely self-contained. It's just telling us that this is not what we usually think of as friction. And that's why all these things are in quotes. Okay, so if C is 0, then E is constant, and there we're fine. We can solve everything, and in fact, you may have learned this. How many people took more than one mechanics class here? You may have learned these techniques. You may have learned to do just these things. E is conserved, and let us put the phi of u of psi on the other side. Let's then take the square root of this term here, and we end up with, let us integrate in this variable psi, and we end up with, okay, you see that we can integrate this. This phi is a known function, right? This is supposed to be, this phi is not an abstract function. This is a function that we have, that defines our problem. The phi is a known function. And we can, and the E is a scalar, it's conserved, it's a number. So this integral should be able to be done. I don't mean done analytically, but it exists. The old guys used to tabulate these all the time. That's what if you had been an old-time mathematician or physicist or engineer, that's what you would have done. It was tabulating these kind of things. So you see that you can get psi as a function, okay, if the purpose is to get u of psi, which you're going to see it might be, you would consider that to be a solution of this. You're looking for u of psi, looking for the shape. Here, you haven't quite gotten that. You've gotten psi as a function of u, even if you could do this integral. This is an elliptic integral if this is a cubic function, which it often is. Again, those old guys, they knew how to do this, and you can look up in tables, and you can probably do it, and you can get psi of u, and if you could invert it, which you can't, again, analytically, but in your mind you can, you would get u of psi. And so that would be the solution to the problem. So what we're looking for is not another way of solving the problem, but a different way of thinking about it. What I always say about dynamical systems, it's not an object of study. The purpose isn't to solve the problem, is to understand and to get certain tools and certain way of thinking about things in terms of fixed points or traveling waves or limit sets. So let us look at another way of looking at it. Dynamical systems approach. We are already used to the idea that we're going to consider psi to be time. And now, remember what we said about this. This is a second derivative, and we already said in our first class, we said I said a dynamical system is, looks like this, dx dt